right, a little Beatles for us today as we get into talking about continuity in Calculus 1. Okay, so what we will begin to do is just look at some functions of different types and talk a little bit about what we mean by continuity. And the basic idea is as we look at the graphs, we're looking at whether there's any breaks in it. So just to begin with, if you looked at, so the very first graph we have here does not have any breaks in it. So if you look at this, if you started here, see, I'm sort of drawing this without lifting my pencil. I don't ever have to lift my pencil. So we would say this is a continuous function. There's no breaks in it anywhere to be found. Okay. Whereas the next graph, now this one we usually call a piecewise function, goes like this. If I was to draw this graph, well, I'm lifting my pencil as I'm drawing this. So this has lots of breaks in it. So we would say that this one is discontinuous. Okay. So what we're looking at is just breaks. This one would have like a break at 1, 2, 3, 4 places right there. So it's discontinuous at those particular points then. Okay. Here's another example of some other piecewise functions right here. This one right here, if you went through and if you just kind of traced over the graph, okay, well, it's nice and continuous. There's no breaks. Now there's this solid dot right there, but still no break anywhere in the graph. That's just sort of to show that the pieces change right there, but that still is going to be a function that we consider to be continuous at all the points on the graph. Okay, the next one, you start here, you're nice and continuous, and then what happens is once you get to x equals 0, then you got to lift your pencil, so there's a break like this. What this one's basically saying is when x is less than or equal to 0, you're actually on this line x plus 2, so that's what that is. And then when x becomes greater than 0, then you get on the quadratic, which is x squared plus 1. Okay, so this one would be discontinuous at a particular point. Okay, this one, what we'd say is discontinuous, and it's really discontinuous at x equals 0. Okay, and then the next piecewise function is a good example of something you see a lot. You have a constant function, and this is for every x value except 2. So what's happened is you're nice and continuous, and now you're not defined at x equals 2, because when x is equal to 2, you're actually equal to 3. Okay, so what this point right here is, that's a 0.23, so it jumps out of the line and forms a place where it's discontinuous. So this one would also be discontinuous at that particular point then. Okay, so it's really discontinuous at x equals 2. Everywhere else, though, it's continuous. Okay, then the last example, you have really a circle. So if you were to go through and, or not a circle, semicircle actually. So if you went from -2 to 2, that would be continuous. So we would say this is continuous on the interval -2 to 2. Okay, that's what the graph is saying. That's an x value of -2, that's 2. And what happens in this particular problem is the reason I'm coming up with this. If you wanted to find an x-intercept, what you do is you set the function equal to 0. Okay, then if we squared both sides, we'd end up having the radical going away. We'd have 4x minus squared equals 0. We could add x squared to both sides, and then we can square root both sides, which gives us plus or minus 2. So it has two intercepts on that like that. So that's why that graph looks the way it does. Okay? Okay, so on the next page, we're going to formally talk about what continuity is with a checklist and a more precise definition. So, the definition, a function f of x is said to be continuous at x equals a if this condition holds. So we're looking at the limit as x goes to a must be equal to f of a. If f is not continuous at a, then a is called a point of discontinuity. So to help you understand what this is saying, let's just kind of randomly put, we'll call that x equals a. And we're going to say that this function is discontinuous at that point. I'm just going to give you kind of one example of how this might look. So let's say that that's f of x, okay? And let's say that this is L, okay? Meaning that's the value of the limit. So what you would have in this situation is we would say the limit as x approaches a of f of x would approach L. This would be an example of a limit that would certainly exist because the left-hand limit is approaching L and the right-hand limit's also approaching L, so it does that. However, f of a is going to be some different point. So if we look at f of a, that might be something like m. F of a is equal to m, and since L is not equal to m, that's why it's discontinuous. So what this is saying is it's saying the limit of the function has to be the same as the function value. That's the idea. And then what would happen on this, if I went through and put that dot there and filled in the bubble, then it would become continuous because the limit would be the same as the function value. So that's the idea. Okay, now what we're going to form here is a continuity checklist and show you three conditions here, really. So the first thing is, if something is going to be continuous at a point A, really looking at x equals A, we have to have these three, and that's not tree. That's supposed to be three conditions, must hold. So the function f of A, it has to be defined at A, okay, and it has to be in the domain of f. The limit has to exist, and finally, the limit must be equal to the function value. So you want to get this real clear in your mind what the formal definition of continuity is, instead of just knowing it, kind of informally. So I'm going to show you these three conditions down here. So you can look at this. This is certainly discontinuous. You would say on this first example, you would say that we're discontinuous at x equals 3. You can clearly tell there's a break in the graph there. But one of these three conditions doesn't hold. So first question is f of 3 defined? Well, the answer to that is yes. Okay, and that's because of that bubble right there. Because really, you have a point 3, 1 on the graph. So we are defined. Okay. Next question is, does the limit exist? Okay, that's the problem. Because if you did a left-hand limit, as you close in, you would see that left-hand limit would approach 1. And this right-hand limit, as we're going from the right, it seems like it's approaching 4. So they're approaching different places. So that means no. Okay, and since the limit doesn't exist, then condition 3 wouldn't hold either because you don't have a limit. So when you have a break in the graph like a jump like that, we usually call that a jump discontinuity. It's basically because the limit does not exist. That's why it's discontinuous. Okay, then on the next example, you have a function. It's clearly discontinuous, just informally. It's discontinuous at x equals 2. And let me zoom on this just a little bit here. Okay, it's discontinuous at x equals 2. And let's see why. There's clearly a break there. So the question is f of 2 defined? Yes, it's defined, okay, because you have this solid dot right here. So it's defined. You have the point 2, 1. So it's definitely defined. So that one passes. Next question is, does the limit exist? Okay, well, if you did a left-hand limit, notice that that left-hand limit seems to be approaching 4. And that right-hand limit also seems to be approaching 4. So yeah, the limit exists. Okay, there's no doubt about that. It's okay that there's a bubble there. But the problem is does this limit equal the function value? Okay, this is the one that does not hold because the value of the limit's 4. If you look at your diagram, both the left and right-hand limit are approaching a y value of 4, but the function value, okay, basically what you get is you get f of 2 is equal to 1. Okay, so since that's equal to 1, then they're not the same. So that would be why that would be discontinuous, is because the limit of the function value is not equal to the function value. Okay? All right, the next one, again, is pretty clearly discontinuous at x equals 2. There's a break in the graph right there at that bubble. So is f of 2 defined? Okay, the answer is no. There's no solid dot anywhere, so it's not defined. Does the limit exist? Well, let's take a look. Left-hand limit seems to be going to 6. Right-hand limit seems to also be closing in on a y value of 6. So yeah, that holds. But then the limit is not equal to the function value because the function value doesn't even exist. So in mathematics, one of the hallmarks of mathematics is we can very precisely and formally define things that are intuitive. Okay, it's pretty intuitive and it's easy to tell when something's discontinuous. You look at a break in the graph, but the formality of the definition is what we're after. Okay, now as we move on to the next thing here, so what I'd like to talk about is what polynomial functions look like. And it's kind of helpful if you remember in college algebra what polynomial functions look like. Now, a polynomial, I always just say that polynomials are sums and differences of whole number powers of x. So you just kind of write a bunch of x's out, and then you can put whatever powers on these you want to. And then you can put plus and minus in front of them, and you can put any number that you want in front of an x, or you can leave a number off of it if you want to. So that would be like a polynomial function right there. That's what they look like. And the graph of a polynomial function is really defined by its highest power. And the highest power of x, we call that the degree. Okay, so if you're doing a degree of a polynomial, it turns out this way. If you have an odd degreed polynomial, then the graph will either look kind of like this. At the endpoints, it'll kind of do something like this. But the thing is, it's continuous. There's no breaks in it. Now, it may kind of twist and turn, do something kind of like this, you know, stuff like that. But the thing is, it's continuous. And if it's an even degree polynomial, then the graph the endpoints tend to turn up, and then you may loop a couple of times like that, depending on the degree, or you may just go straight down, something like that. So they are continuous. So we say a polynomial is continuous for all real numbers. Okay? And since it's continuous for all real numbers, when you spot that you're doing a limit, or considering the continuity of a polynomial function, you're going to know it's continuous. Okay, so you would just say that, and you know, in interval notation, that's just all real numbers. Okay, so that's how that goes. Now, a rational function, what a rational function is it's a ratio of two polynomials. So on rational functions, and they can look different ways, but the thing on a rational function is you basically just put a polynomial on top of some sort, maybe something like that, and then you might have some sort of a polynomial on the bottom. So it's a ratio of two polynomials. So what we say is a rational function, and that's of the form, we usually just say r of x equals p over q, where p and q are polynomials. It's continuous for all x for which x is defined. Not x, where the function is defined, is what I mean to say on that. So it's going to be continuous for all x for which f of x is defined. Okay, whatever that polynomial function is. Let me call that r of x, you know, just to stand for the rational function then. So there's going to be places where the rational function's undefined. It may be a vertical asymptote. It may be a whole. Kind of depends on the situation. Okay, so these are some examples down here. So this first graph that I have right here, and I'll zoom on these graphs a little bit as I go through these. Okay, this is a rational function. Okay, that is a ratio of two polynomials. Okay, if you went through on this one too, you have f of x equals x over x squared minus 7x plus 12. Well, you could factor out that denominator, and if you factored that, you would have x and x, you would have 4 and 3, and you'd have two minus signs like that. So basically, you would be undefined. You would have a zero denominator at 4 and 3. So x is not going to be equal to 4 and 3. So that ends up being asymptotes. So you can see that you have a vertical asymptote at x equals 4. You have a vertical asymptote at x equals 3. So we'd say that this function is continuous everywhere except where it's undefined. So it would be except x equals 3 and x equals 4 because of the asymptotes. Okay, the next one, if you look at this, now this is continuous. So if you went through again and if you just sort of trace that out, you're not ever lifting your pencil, so it's going to be continuous on the interval a to b. So since that has a dot, we're going to do a bracket there and say bracket a. And then b has a bubble in it, so we're going to use a parenthesis on that then. Okay, so we're going to have parenthesis on b like that. So it's continuous on that interval. And then the next one's just opposite. This one would be a hole there, so it's continuous. We wouldn't include the a. It has a solid dot there, so we would include the b. So that would be what we say, where we say it's continuous. Okay. All right. Continuity at endpoints is the next thing I'll talk a little bit about here. And we can be continuous from the left. This is kind of a definition of continuity from the left. Okay, so what we're saying on this is we say it's left continuous at a if the left-hand limit, and that's the key, it's the left-hand limit of the function is equal to the function value. Okay, so it's equal to the function value at x equals a. That's a left-hand limit. And then we're continuous from the right, or right continuous. Again, you have a right-hand limit because of the plus sign. Again, it's basically saying the same thing. The value of that limit is going to be equal to the function value at x equals a. So that's how you're going to know that that one is continuous, or right continuous. Okay, so we're going to look at some diagrams for continuity, okay? And I'm going to zoom on this a little bit so we can, see the endpoints on this. So first of all, if you kind of look at this part of the graph, I'm just going to kind of trace this out in green here. Okay, so we're definitely continuous on that part. This is the green part of the graph. And we're looking at x equals 0, and then we're looking to the left of x equals 0. So what we would say on this is we would say that this is continuous on the interval negative infinity to 0, and then we'd close with a bracket at 0 like that because there's a solid dot there, so we would have that. And that's implying that that function goes on forever to the left. Okay, then I'll shade this in red here. So we have an open bubble. That, of course, means we're undefined at x equals 0. And then we're continuous. Okay, I'm not lifting my pencil. There's no breaks from there on out. So what we would say is this is continuous on the interval from 0 to infinity, like that. And then we would say it's not continuous at x equals 0. That would be where you have the break in the graph. And the reason it's not continuous is because the limit as x approaches 0, a two-sided limit of f of x, does not exist. Okay, so you got a place where the limit does not exist. Okay, the next example, we have a semicircle. And again, I want to just kind of reiterate, if you were finding an x-intercept, I did a similar problem to this a little while ago. If you set that equal to 0 and squared both sides, you would get 9 minus x squared equals 0. 9 equals x squared. Or you'd end up getting plus or minus 3. So this graph has endpoints at negative 3 and 3 for that reason. And it's because the domain of this thing, basically the domain of this function, falls between negative 3 and 3. Okay? So what we would say on this, now we're kind of looking at the continuity here. So the idea is this one would be continuous. First of all, it would be continuous on the interval from negative 3 to 3. Okay, now we're talking about left and right continuous like this. So if you look at this endpoint right here, this one, if you're coming from the right, just kind of closing in from the right, you're going to be continuous. So we would say this one is going to be right continuous at x equals negative 3. And then this point right here, if you looked at it, as you kind of close in from the left, and you just kind of keep closing in, you're getting closer to that function value 0, we would say that one is left continuous at x equals 3, like that. Okay? And then the next thing I want to talk about is greatest integer function and kind of give you an idea of that. Okay, so greatest integer functions generally denoted with these brackets like this. Okay, most of the time they're written like that. And it's the greatest integer n such that n is less than or equal to x. Now remember what integers are. An integer is, positive and negative whole numbers. You can just think of it as the numbers on a number line when you're creating a number line. So that's what integers are. So when you see this symbolism, you're looking for an integer. The answer is going to be an integer that's less than or equal to the number within the bracket. So if you were to plot out 2.5, the integer that's the greatest, that's less than it, is going to be 2. Okay, so the answer to that problem would be 2. Okay, and then you have the next one, 0. Okay, well, that would be the integer that's less than or equal, and the key is equal, so that would be equal to 0. And then if you went to negative 2.5, which is located here, the nearest integer that's less than it is going to be negative 3. So that's all you're doing. What you're doing is just taking an integer that's to the left of it on the number line, the closest one, and if it's equal, it's just equal to itself. So greatest integer functions, this would be an example of what its graph would look like. So if you kind of look at, let me just close in on an interval here just to kind of help you understand how the graph goes. If you were to look, kind of zoom in on that piece right there, okay, what it's saying is, you think of all those numbers between 0 and 1. If you did the greatest integer of 0, that's equal to 0. That's why that is a solid dot. But then if you go to the greatest integer of 1, that jumps up to 1. Okay, so that point jumps up there then. Okay. However, all the numbers, the decimal numbers between 0 and 1, like if you did the greatest integer of 0.5, that's still 0. Or the greatest integer of 0.7 is 0, and so forth. Okay? If you're in decimal form, you're just kind of, for positive numbers, you're looking at that number before the decimal. So that means all those decimal values would just be a constant function, so it would look like that. So what happens on this one, if you were going through and looking at your limits on here, okay, this one is a left-hand limit. The first one's a left-hand limit as x goes to 0 from the left. That means you're down here. So if you just kind of closed in, that limit is approaching a y value of negative 1. Okay, but then if we did the right-hand limit as x approaches 0, coming from the right, now if we're coming from the right of 0, we're going to be in here. So that means that limit is going to approach a y value of 0. And then since the left and right-hand limit don't exist, go to have different function values, then we would say the two-sided limit does not exist. Okay, so that's how a greatest integer function works. Okay, let's look at some graphs and kind of continue to just look at this informally for a few minutes here. So, this graph right here, let's just find all the places it's discontinuous. This would be one place right here at x equals negative 1. So we're definitely not continuous at x equals negative 1. We also have a break at x equals 0. And we have a third break at x equals 2. So we would say f of x is continuous everywhere except at negative 1, 0, and 2. Okay, so let's look at the reasons why. So as we kind of go through these one by one, let's look at why it's not continuous at x equals negative 1. Okay, looking at our graph, and remember, we have a checklist. I'm just going to write this checklist at the side. First of all, f of a must be defined. So the function has to be defined at the point you're interested in. The limit, as x approaches a, that's a two-sided limit, must exist. And then the third condition for continuity is the limit as x approaches a of f of x must be equal to the function value when x is equal to a. So if you look at x equals 1, if you just kind of zoom on this part of the graph right here, okay, if you look at the checklist on here, okay, well, it's defined. Okay, so you basically have the point. You would basically have f of negative 1 is equal to, I think that's a 2 there. So it's defined. the limit also exists. So if you did a limit as x approached -1, that does exist. But the problem is it's the function value is not the same. So the idea is this point right here has a function value. Let me write this like this. Again, at this particular point right there, f of -1 is equal to 2. But look at the limit. The left-hand limit is approaching 1. The right-hand limit is also approaching 1. So that would mean that the limit of f of x as x approaches -1 would be equal to 1. So those things would not be the same. Okay, so what we would conclude on this then is we would say the limit as x approaches -1 of f of x is not going to be the same as f of -1. Okay, they're both basically different. Okay, so that would be the condition that fails. Okay, then if you look at the next situation, if you look at x equals 0, okay, what's going on that is the function is defined. I mean, that's a point. You're defined at that point. Now, the next question is, does the limit exist? Well, that's what fails, is because if you look at this, you know, the left-hand limit is going to 1, the right, or 2, the right-hand limit's going to a different place. So we would say the limit as x goes to 0 of f of x does not exist. So the limit doesn't exist there. That makes it a jump discontinuity. And then the last place is 2. And if you look at x equals 2, well, you got this bubble here. So that means we are not defined. So what fails on that is condition number 1. You're not defined. So you would just say f of 2 is not defined. So that would be the technical reasons why those limits, why those points, that function is discontinuous at those 3 points. Okay, next one is just sort of some definitions. If you look at this graph, so what you have in each of these situations, if you just sort of have a hole like that, the function, the limit exists, but you have a hole, we usually call that a removable discontinuity. Okay, and then if you have this situation where you got a hole and like this, the limit doesn't exist basically, we call this a jump discontinuity. Okay, so this basically says the one-sided limits exist but they're different. So if you looked at this, clearly the left-hand limit approaches a different number than the right-hand limit, so it's a jump discontinuity. And this one you have at x equals 0 right here. What you really have in here is you have a vertical asymptote. Okay, so in this case, what we call this is we call this usually an infinite discontinuity. And that's the idea, is you're going to end up having the limits may or may not exist in this case. Okay, in this case, the left and right hand limit would go to infinity. There would be cases where they would go to different places, and then the function's undefined there. So you have an asymptote. That's the idea. So what you have here is you have a infinite one-sided limit. Okay. All right. Going to the next piece here, we're going to look at some individual examples now. We're just kind of looking at a function and beginning to look through things. So this is a function here, and you've got this place here where you have some denominators. So what you're going to have to figure out is, you know, what's making that function undefined. So that's the first thing we're going to do. So we're going to look at where it's continuous and where it's discontinuous. The first thing we're going to look at is let's just kind of work with this function. And one thing that's going to be pretty important on this is that you factor that numerator. That numerator is a difference of 2 squares. So that factors as x plus 1 times x minus 1. Then you have x minus 1, and then you have x minus sine x. Okay, so one of the things we've talked about in a previous section is you're going to notice, let's kind of look at where we're undefined first of all. So clearly this function, there's two places where it's undefined. Okay, you could take, you take this factor and you take that factor and you set both of those equal to 0. So if you took x minus 1 and set that equal to 0, well, you would get x equals 1. So we would say we're undefined at x equals 1. Okay, so that would be one thing. Now, if we do the next one, you got to think about this a little bit. You have x minus sine x equals 0, and you really can't factor or anything on that. There's several things you could do. You could try to square both sides. You know, to me, this one is just kind of a good one to analyze. I'm going to look at this a couple of ways. First thing I'm going to do is look at this on a unit circle. So I'm going to pull up a unit circle here. Okay, so presto, there's a unit circle. And what I want to look at is, now see, x, this thing right here, that's an angle. That represents an angle in radians. Okay, so does that. Okay, so what we're looking at is on a unit circle, where is the angle equal to the sine? Now, the sine is the y value. Okay, so the y values, if I just kind of go around the unit circle, you know, everywhere, all these y values are the value of the sine. So one thing that we know on here, just by looking at this, is the sine of 0 is equal to 0. So that would be one place where it exists. This angle is the same as the y value. That's the only place, though. If you look at this, pi over 6, that's not the y value. Pi over 4, that's not the y value. That's the only place where that happens. So that means that x has got to be equal to 0. So what we would conclude just by looking at the unit circle would be that. Okay, we would get basically on this that x equals 0, you're also undefined. Okay, like that. So we have concluded this, and we have concluded that. Okay, so those are the two places this function's undefined. Okay, another thing I'm going to do with this, I'm going to pull up my graphing calculator and show you that. So what I'm going to show you with my calculator here is we're going to graph the two sides of this equation. So I'm going to graph, first of all, and you want to make sure that you're in radian mode. So be sure you're in radian mode. And we're going to just put y equals x in, okay, which is a line. Then we're going to put the other side of the equation in, sine x. And then for a window, we're just going to go, it doesn't matter, let's go like something like -5 to 5 or something like that by a scale of 1. And then for the y values, let's just look at maybe -3 to 3, because what it's going to do is it's going to graph the sine and that line. So your line y equals x is coming out right now, and then you have the sine wave that's going to start coming out. Okay, there's only one place where those 2 points intersect, and that intersection point is right there. So that's the idea, is x equals 0 is the only place where that exists. So you can look at these things oftentimes analytically as so if you look at my graph again, I just want to make sure that you understand how that goes. This is y equals x. Of course, that's y equals sine x. Okay, the only place where they're the same is right there at the point 0, 0 is the only place they intersect. Okay, so we've made the conclusion. We now know where this function's undefined. That's kind of a key part of this problem. So those are the potential areas for discontinuities. Okay, well, now one thing that happens on this is notice that when we do this, that cancels. So that's not a vertical asymptote. That's going to be a hole. Okay, you're going to have some sort of an asymptote occurring right there. Okay, so that's going to be the idea. So we're going to examine this, and then we'll look at this graphically as we go through this then. Okay, so at what values of x is f not continuous? Well, it would be the two places where it's undefined. So we said that x equals 0 and x equals 1 would be the two places you're undefined. Okay, so so f is going to be continuous wherever the function is defined. Okay, so it's continuous everywhere else. Okay, just the two places where it's undefined. Therefore, we'll say f of x is continuous wherever it's defined, except at x equals 0 and x equals 1. So what we're kind of looking at here is the denominator. So it's therefore it's going to be f is continuous wherever this is not equal to 0. Okay? So at x equals 0 and x equals 1 we're undefined. So to determine the type of continuity, we'll just examine the denominator basically. All right, so to determine the type of discontinuity at x equals 1, you're basically going to evaluate a limit. It looks like you're going to have a hole in the graph. So what we're going to need to do is we're going to need to do a limit on this. Okay, so we're going to go ahead and do the limit of this function. We're going to go ahead and do the limit as x approaches 1. This is where we seem to have a hole there in the graph. So let's analyze that limit. We should be able to just use our calculator to help us a little bit with this too. So we're going to do the function, don't worry about where it's, you can cross that out. So we're just going to do the limit of 3x squared plus x over x minus sine x. Okay, so let's just plug in the value on here of 1 and let's see what we get. So that's going to be 3 times 1 squared plus 1 over 1 minus sine x. All right, and that's going to be 3 plus 1 over, and then let me take my calculator. We really need to just do this on the calculator. So what you'll have is just clearing this, and if I just do in radian mode, if I do 1 minus the sine of 1, that will give this number right here. So I'm just going to round that off. Let me get that so it stays up here. So I'm just going to write that as 0.1585290,152. And then I can do the rest of this on the calculator. I can just, and actually I could do this in one step. I could just go, and that's really the way I ought to do that. I need to write that as a sine 1 like that. So if I just go 3, if I just go 3 plus 1, let me get this. There we go. 3 plus 1 divided by parentheses 1 minus sine 1. Okay, like that. That gives me, let's see, about 9. That's about what that looks like. Make sure I got that put in there right. Yeah, okay, it looks like I missed this one thing right here. I was looking at this and that didn't look right to me, so that's x plus 1 is what that should have been. So that's 1 plus 1. So that ends up being this. Okay, now let me get my calculator out and let's fix that then. Okay, so let me clear this off and then we're just going to go 3 plus 2. And then divide by parentheses 1 minus sine 1. And let's see, I think that gives around 15 or something like that. Let me take that extra parenthesis off. Okay, yeah, so that's about 15. So we'll get, that's approximately 15.6. Okay, so what that means is, we know the limit exists on this, but we're going to have a hole at that point right there because that it dropped out. Okay, all right, so let's move on from this point. So we put this in the calculator, and I'm going to go ahead and get my calculator out and put it in, and you can do the same. Okay, so I got my calculator up here, and I got it put in the graph like this. You'd have to put this in your calculator like this, basically. You'd have to put in the 3x to the second, and you have to say plus, and then you have x minus 1. Let me put this in here. Okay, so you're going to put this in your calculator like this. You've got to put in the 3x squared. Okay, then we want to put in the x to the second minus 1 like that, and then divide by. Then you've got to kind of double up on your parentheses because that whole denominator needs to be in parentheses. So you're going to say x minus 1 times x minus sine x, and then you've got everything the way it's supposed to look. So I'm going to go ahead and get that put in my calculator. Okay, and then I've already put a picture of this on the calculator, so I'm going to set up the window kind of like this. Let's say -5 to 5. And then let's go for the y's. Let's go so we got a pretty good viewing window. We're going to go like -100. Whoops, I got that wrong. That's -100 goes there. Okay, then we're going to go to +100. And then we'll scale that maybe by 25, kind of like I've done here. And then I type graph, and you should get a graph looking like what I've put on your handout. And you'll see that you have an asymptote there, and you also see that you have a hole there when you look at that then. So the idea with this thing is, just like we thought we would have, we had a hole at x equals 1, and then this limit, and we crunched this out when we did the limit of the function as x approached 1, that did exist. It was about 15.6 approximately. Okay, then we had an asymptote here. So you can see that we have a vertical asymptote on that. So that would be the two places where that function's discontinuous. Okay? All right. So the type of discontinuity at x equals 0, that would be the one that has an asymptote. We would have what we call an infinite discontinuity. Okay, and that's as the limit would approach -infinity from the left, and it would approach +infinity from the right. Okay, now we're going to go on to the intermediate value theorem. Okay, next thing we want to go over is what we call the intermediate value theorem, which is actually very simple. It's very logical. It just says you have a continuous function on an interval a, b, and L is a number between f of a and f of b. Then there exists at least one number c in the interval a to b that satisfies the condition that f of c equals L. Now this diagram should show this pretty clearly. You're looking at an interval from a to b, and you have a graph that's continuous. You can see there's no breaks in that graph or anything. And f of a and f of b are different values, so this would be f of b. That's b follow up to the function, that's the y value. And f of a would be just the y value when f of a equals when f of a. And L is just some number, okay? And if you drew over to the function and down, then that would force C to be in the middle. So it's just basically C is in the interval A to B. So it's between those two like that. So it's the only thing that could follow on that. Okay, and then we have kind of a consequence of this that just says if f is a continuous function, f is continuous on A to B, and then f of a have opposite signs, then there has to exist a number in a and b such that f of c equals 0. So what this is saying, like in this particular problem, the interval would be from 0 to 3. We're interested in 0 to 3, and in this case we have f of 0 equals 4, so it's a positive number. And in this case over here we have f of 3 equals -4, so it's a negative number. So since you have a positive function and a negative function, there has to be a place where it crosses the x-axis. That's all that's saying. So you would end up having this function value would be equal to 0 right there. Okay, and then this is the opposite situation. You have a interval again for an interval 0 to 4. F of 4 equals 6, so that's some positive number. And then you have f of 0 is, oh, my cat is just like going crazy here. So, what's the matter, cat? You're like, act like you're really angry at something. Okay, sorry about the cat. Okay, so we have f of 0 equals some negative value. So in this case, notice that, well, we crossed 3 times. But the point is you have to cross at least 1 time. Okay, so that's the idea. So this will be the first part of the discussion of continuity. The second part, I'm going to do a lot of examples specifically with functions.